Hello everybody, I'm Dave Dugan. I'm the president of EBTRON. This portion of the presentation I'm going to give today is on controlling building systems. All right, and so what we're going to cover in this section is what your airflow measurement requirements are. We're going to look at your special considerations for demand control ventilation. I think there's a real opportunity there to improve DCV. And then we're going to go into some integrated dilution, ventilation, and pressurization control strategies. Okay, when we talk about improving system control, it's really important. I feel like too many buildings really aren't functioning as well as they should. And I work with a lot of test and balance people, and we kind of all agree on this. We really got to get a better handle on measurement and control of these buildings. And I'm just going to break down the basics here that we like to talk about, and it's controlling outdoor airflow rates. There's a lot of reasons to do that. One is to maintain and demonstrate code required ventilation is maintained. And some people think, well, we just can do that once and just set it up and forget it. But really, it's not true. In other presentations that I give, I talk about fan speed issues, wind pressure, stack pressure. If you're not really familiar with those and how they affect intake flow rates, you should really take a look at one of those presentations, as well as damper issues. We have hysteresis, binding, and deterioration. And in reality, uncontrolled outside air intakes truly will vary 50% or more of the desired set point. And that's just not acceptable. It causes temperature control problems, humidity control problems, IQ problems, pressurization problems, energy waste. It just goes on and on and on. Okay. The other thing that we need to do, and we need to think about it more today than we used to. We always think about healthcare facilities and supply airflow rates because we're concerned about room air changes. Okay, but some of the new energy changes that we've seen. And requirements for like standard 241, for IRMM mode really talks about, equivalent ventilation. So clean air equivalent ventilation. And so that if I was to do a presentation on that right now, we'd see that we have outdoor air for dilution, but we also have the potential for clean air for dilution that's recirculated. So it's not just now measuring and controlling outdoor airflow rates, it's measuring and monitoring and verifying supply airflow rates when people are making claims of using clean air equivalents, okay? And then the other thing that's really important is controlling building pressurization flow. And, it just depends on why. Again, in healthcare labs, we kind of really understand this. In occupied spaces, office buildings, schools, universities, we don't always pay as much attention as we should. We need to be able to maintain compartmentalized building pressure. The only way we're really going to pull that off is by controlling airflow rates. And depending on where you are in the country, if you're in a climate with a lot of moisture, you really have to do this, or you're going to have mold and fungal growth problems. But it's not just that. Even in dry climates, you're bringing in untreated outdoor air before it ever crosses a filter. So there's things that you have to think about here. All right, I'm going to go through this relatively quick. Okay, so you might have to go back and take a look at some of these slides again, or take a look at this again. But basically, when we're doing flow measurement for control of both dilution, ventilation, and pressurization, so it's kind of like an all air control strategy, which is what we like. We either have systems that are supply relief or DOAS that don't have a recirculating path, or we have air handling units that have a recirculating path. So on the left side of the screen, that's your supply relief and DOAS systems. So we're going to measure the total outdoor air and the total relief. And hopefully we're measuring these in good locations, because this differential is really difficult to do properly. So you have to have good measurement locations. The beauty of some of these DOAS and some of these systems here when you're doing this is that you are dealing with filtered outdoor air, so don't go before the filters if you can avoid it. The other side is a little more complicated, and there's a lot more choices, the right side of the screen, which is recirculating units. So recirculating units, we're going to have to do a combination of supply and return flow measurement as well as at least minimum ventilation or minimum outdoor air, okay? So, those are going to be the measurement points that we're going to have, all right? Now, what is difficult to try to figure out, what people have problems with, is, we talk about differential flow control for pressurization. And so the question is, how much air do I need? What do I need? And so, basically the pressurization flow is basically going to be the difference between your mechanical ins and your mechanical outs. All right, you need some pressurization flow if you want to maintain, say, a slightly positive building. So what is it? Well, you can estimate it, okay? And different people have different numbers here. I mean, my numbers, depending on the leakiness of the building, have always been between 0.02 and 0.05 CFM per square foot of floor area. But it's really a rule of thumb that we use, and it's far from exact, okay? The tighter the building, the smaller the number, all right? But that's kind of the range of what you got to be thinking about. Some people think it's higher. The higher it is, the leakier your building is. The lower it is, the tighter your building is. The lower it is, the harder it is actually to control. Okay, you could use computer models. Some folks will do computer models and estimate leakage that way. There is a test that we had done. It's kind of like an envelope leakage test, but we've actually done it with the air handling unit and our equipment. Okay, and so that we actually measure pressures, and then basically look at the differential and extrapolate. We do it at kind of a higher pressure, not enough to damage the building, but a higher pressure than we would operate, and then kind of extrapolate it down to what our operating pressure is. And I've done that on our own building, and it's actually worked out pretty well. But basically whatever it is, the bottom line is your set point is equal to whatever this pressurization flow you figure out, calculate, and any local exhaust you have. So that's procedure one, okay? That's option one. Option two would be field measure it. Basically, there's, again, the balancing professionals are going to have their ways. I'm, again, doing things that I would do. We open all interior doors of the pressure zone. We basically keep our, we look at how we want to set up our exhaust fans. We install temporary pressure sensors or permanent pressure sensors across the exterior surfaces, and then we adjust the differential till we get the pressure that we want. Okay, that's another way that we can do it. Okay, any rate, there are two different techniques you can use. Now, when it comes to the outdoor air set point, because you have to have both, right? We're going to have the differential set point and outside air set point. So, if you're doing it, if you're not doing DCV, okay, you're not doing demand control ventilation, you're going to be doing it based on design occupancy. So it's a fixed set point, right? You're going to be doing that. You should be doing that on low occupant density spaces that don't have, for sure. And you should consider doing that on high occupant density spaces that don't have a lot of variability in population. And so you're looking at your code really to determine what the required outdoor air is. And, you look at what you need for pressurization. Okay. A lot of times people ignore the two. All right. You choose the greater. I mean, there are cases where, your pressurization requirement exceeds your outside air requirement. Okay. It can happen, but you choose the greater. And, that's your outside air set point. It's pretty straightforward. DCV is far from straightforward, and it's getting more and more complicated. And honestly, I feel like a lot of people don't really understand it and don't really understand how to make this work right. So, we're going to take a look at the code required ventilation for the maximum population. And we're going to look at the pressurization again. And then we're going to take a look at this, and we're going to look at what the lowest expected occupancy is. And now again, it's another greater than. I cannot tell you how many times I see people do DCV and reduce the outdoor air flow rate below what they need, below their exhaust and pressurization requirements. So they end up running a building negative and not even knowing it. Okay, that's one of the advantages of measuring and controlling airflow rates. You actually know what's going on. Okay, now when we get into DCV, I've thrown these slides into this control portion just to reiterate some things, okay, and make sure everybody understands. DCV, demand control ventilation, is required in a lot of areas, okay, and if you're dealing with ASHRAE 62, okay, ASHRAE 62 compliant DCV, what's the definition? Well, it's what I have there in red is the most important thing. For DCV ventilation zones in the occupied mode, breathing zone outdoor airflow shall be reset in response to current population. It's really not based on CO2 levels. Whenever anybody's using CO2, they're doing it for estimates, but they're not really to the letter meeting the requirements of standard 62 the way it's currently written. And so when you look at the right-hand side here, it's very simple logic. It's like, hey, I measure the population, okay, and I say our census, but there's different ways you can measure the population, a lot. I'm not going to go into them today. You calculate basically what the outdoor air requirement is. It's always good to set limits in case your population counting devices have errors. So you may have a lower limit that has to do with exhaust that has nothing to do with population, and the upper limit, if you've hit the design outdoor air, the design population, you're good to go. So you set limits, which is what I do next there, and then you have an outside air set point. It goes into whatever your control strategy is, and we're going to talk a little bit about control strategies, okay? And you measure the outside air, and you have an output of that control loop, and it could be as simple as modulating a damper, and it could be a more complex sequence. But the bottom line is, if you wanted to do DCV the way that standard 62 tells you, that's what you do. And the beauty of that is if you did it right, it works on single zone and multi-zone. I don't have multi-zone in this presentation today, but I can talk to you about if you knew the number of people in the critical zones on a multi-zone system, recirculating system, and you knew the airflow rate, you know the people, you know the population there, and you know the airflow rate into the zone, you calculate the ventilation efficiency in real time, and you figure out how much outdoor air you need. It's great, That's the beauty of measuring the population. I just don't understand why that's not the norm, okay? What seems to be the norm, and seems to be getting more and more traction, is using CO2. But CO2 is so misunderstood. It's unbelievable to me. I mean, I've been talking about CO2 for over 30 years now, and writing about it, and just basically beating my head against the wall, okay? Really is what happens to me, because it's like folks just don't understand why they're doing this. And it's like, are you measuring CO2? Why are you doing it? Are you measuring it because it's a contaminant, or you're measuring it for some other reason? Well, you're not measuring it because it's a contaminant. It's not really considered to be a contaminant of concern until it gets over 5,000 parts per million. And that rarely happens unless you really have cut back your outdoor air and the building's super tight, okay? And you've got a lot of people, okay? Rarely are you going to get over 5,000 parts per million. And if you know anything about CO2 DCV, at least, up till recently, most people think about maintaining about 1,000 parts per million or something like that. So it's like, why are you doing it if it's not a contaminant? Well, I've been doing this for a long time, and it amazes me how many people I talk to that don't know why they're doing it. So I'm going to make it simple for you. I'm going to tell you why you're doing it. First thing is, and it's a problem, and I'm not going to cover it today. I have other presentations that cover it. We've assumed steady state as long as we've talked about CO2, all the way back to the beginning days of ASHRAE 62. Steady state, steady state, steady state. Steady state means the population's constant and the amount of outdoor air that's coming in is constant. But no, we're applying this on a space there, the population varies, and you vary the outside air. So really the steady state model is not valid, but everybody uses it, and we might as well use it here to explain why we're doing this. So here we have, when you're at steady, the reason people use it, it's really easy. Because, you know, hey, if you're not assuming steady state, you got to look at the rate of change of the CO2 level in the space, and you got to look at the volume of the space. And that's a lot more complicated. So why should we do that? Okay, we're just going to assume steady state. So when you assume steady state, the volume of the space doesn't really matter. So if we take a look here on the left, that's the outside air coming into the space, all right? And to make a steady state equation, we just make an equation where all of the basically, it's dimensionally consistent across. So CO VOZ, what's CO? It's the outdoor air CO2 concentration. VOZ is the outdoor airflow rate, okay? So that's I call it a goes into. That's a goes into. Another goes into is based on how many people are in a space. You know, we produce CO2 as a byproduct of respiration, so we're adding CO2 to the space. The more people there are, the more CO2 goes into space. I will say we'd have to make an assumption of how much CO2 we're producing, and again, I have another presentation that would go into detail and show you some of the real problems with the assumptions that we've made, but for now we're just going to say, no, that's another goes into. And then of course you've got the goes out of. So the outside air that came into the space is either going to be force exfiltrated, relieved, or exhausted from the space. But it's going to be at the new elevated indoor CO2 level instead of the outdoor CO2 level. So C indoor and VOZ. So you have an equation. You can mathematically rearrange that equation, and what do you get? Outside air CFM per person, VOZ divided by P. That's why we're doing it. You measure CO2, it's a proxy for estimating outdoor air CFM per person. Excuse me, there's a lot of errors associated with that, okay? Now, one of the errors that I like to look at, which is just one of many errors, okay, just has to do with measurement error. The other errors, which I'm not going to go into in this presentation, have to do with CO2 production errors of the occupants, and it's based on their, basically age, their weight, their diet, your activity level, and it's significant, okay? But, we're not going to do this today, okay? So you have this response here. The black line is how much outside air standard 62 required for compliance. This is for a classroom, okay? And then the red is ideally, if you maintain 1,000 parts per million, the red solid line is how much you would be providing. And all I'm doing here is putting 100 part per million uncertainty on the CO2 measurement in the space and 50 part per million uncertainty outdoors, and you get all this surrounding scatter. Okay, so it's significant, okay? In this example here, you could be 70% over ventilating unless you're in, if you're in, you'd be in CO2 alarm if you limited it. And what people do is they do try to limit it, okay? They try to limit it with basically fixed dampers, okay? But when we talk about fixed dampers, which is not part of this presentation, but a reason why you need to actively control outdoor airflow rates, dampers, stack pressure, wind pressure, and if we have variable speed fans, and this is not just recirculating systems with the variable speed fans, it can be DOAS serving multiple ventilation zones, okay? You're going to have fluctuations of your outdoor air that easily exceed 50%, okay? And on the high end, you're wasting energy, but you're also creating potential thermal comfort issues, pressurization problems. On the low end, you're underventilating, IQ problems, pressurization problems. And this is why we have to get this under control. The way we're currently doing it, okay, it's not under control. And that's a problem, okay? So the way we're going to get it under control, I show you two strategies here. One is called deadband control, which people are using today, but they're on the left, they're using it with fixed dampers. So with fixed dampers, it's got all the problems we talk about with dampers and flow rates, okay? Lots of variability, and it has no way to deal with variable speed fans, okay? Whether it be, again, on the intake of a recirculating unit or at multiple ventilation zone, DOS delivery points, okay? So it goes between a min-min and a min-max. It's really what's going on there. The way that you improve this, okay, is you're actually controlling the airflow rate of the min-min and the min-max. You're not just relying on damper positions. It's almost the same logic. You're just adding one more step, which is to control the flows. It's much better. The one on the right is for people that want to do modulating control. Modulating control means I'm going to modulate the outside air to maintain my desired set point, okay? And so in that case, it's really a very similar strategy for those of you that get into controls that you do on a VAV box for temperature control, okay? So in this case, we're going to measure the CO2 level, compare it to our set point. It's going to go into a control loop or a just simple reset loop that outputs an airflow set point. It's going to compare it to the min and max. If it's under the min, it's going to set it to the min. If it's over the max, it's going to set it to max. In between, it's in between. And that set point goes into a outside air control loop where you measure the outside air, and then the output of that is either something as simple as modulating a damper or a more complex sequence, okay? So that would be a big significant improvement on today's traditional fixed set point, say 1,000 part per million CO2 DCV. What you may not be aware of is that there's a lot, because of the steady state problem and because of the CO2 production rate problems, the individuals, the variability, ASHRAE's trying to make an improvement to the way that many of you do CO2 DCV. I actually think it's not going to be an improvement, okay? Just because of some of the things that I've seen and when I look through it, the way they've calculated certain set points, there's still going to be a lag problem, but I think there's going to be a real big problem in verifying that this is actually working. But basically what 62 is doing, it's this addendum AB, it was just released. It basically says that you're going to do a reset of the outside airflow rate based on the CO2 level, starting at the ambient or outdoor CO2 level up to what you expect the maximum design CO2 level to be. And it sounds good, and a lot of people, I think, buy into it that were involved with this, bought into it because they're like, yeah, this sounds good, this is better than what we're doing. But there's a lot of problems with this, okay? I'm going to show you the way that I would do it, all right? Which is probably not the way they're going to tell you to do it because, but that's okay, all right? I mean, basically all it's saying, it's a linear reset of the outdoor airflow rate to the CO2 level. So, I've just looked at this space, I've calculated out at ambient or 400 parts per million, assuming that was the outdoor CO2 level, what the outdoor air set point would be, and I go up to the maximum design population and look at what the CO2 level would be. It's the same classroom example I've been using, okay? And basically, if I were to implement AB, which I think this is a good way to implement AB because it doesn't have to deal with damper problems, damper linearity, handles fan speed changes pretty well. It's not that complicated, okay? You measure the CO2 level. I got two boxes to do this calculation, but you're gonna based on the CO2, it's just an equation of a line, okay? You're gonna measure the CO2 level and calculate what the outside air set point should be. You're gonna compare it to limits. The minimum might not be the ambient. The problem with the way it's written, and you kind of have to read between the lines, is like in this case, well, the ambient is like 120 CFM, okay, of outdoor air. Well, what if you had 200, 300 CFM of local exhaust? That should be your min. Okay, so you're going to do this by putting an airflow measurement and doing this kind of strategy here to set limits. And of course, you don't want to go above the max. And the way the standard is written is you don't have to go above the max. If you can demonstrate that you have the maximum design outdoor airflow, you can be in CO2 alignment, alarm, and comply with the standard. So I kind of like this method. What it does is, if you look at the graph on the right, this AB method has a tendency to overventilate a little bit at the mid populations. I think that's okay. The problem with it is the CO2 levels are variable. There's going to be no way for anybody to know without counting the number of people if the system's really working or not. Your CO2 set point can be anywhere in this case between 400 parts per million and almost 1,200 parts per million. And there's no way that you're going to know that it's right. I mean, that's crazy to me. Okay, I think it's terrible, actually. So that's why if you look at my comments there, say, hey, the calculated zone ventilation rate most likely will not correspond to the actual ventilation rate because CO2 ventilation codependence on uncertainties. That's a really huge problem. I think you're going to find that folks are going to try to do this just by simple proportional reset of dampers. That's not going to work. It's really not going to work on variable speed systems, okay? And then, like I said, there's no way to verify it. But if you run that logic that I showed you on the previous slide, it's, I think, the best way you're going to be able to do it. Another way, though, to do it that we've been kind of promoting for 20 years, but I guess to deaf ears because nobody listens, is, hey, if you've bought into this steady state relationship, which is wrong, but if you've bought into this steady state relationship and you go back to it and you decided that you're going to be measuring the outside airflow rate, okay, well, you have one more piece of that equation. And that one more piece of that equation now allows you to estimate the population. And so what you see there is the control logic for calculating, for the outside air control, estimating the population using CO2 and outside airflow. Both these methods that we just talked about don't work very well on multi-zone recirculating systems. That seems to be completely ignored as well. I don't completely understand that other than if you look at the math involved in it, it's somewhat complicated, so not everybody may be looking at the math. I have it, so anybody who sees this who says, hey, can you tell me what the problems are? Yeah, I can dig all this out, okay? But anyhow, when you look at what we're currently doing, which is on the left, which is where we're at, we're doing, basically fixed set point, CO2 DCV. We're setting limits with dampers, okay? That's how we're doing it, okay? So you have all this uncertainty on the high side. You got problems with turn down. So you got, basically, you don't really know where you're at, okay? And when you take a look on the right there, it's using the same uncertainties of the CO2 measurement, but now it's, it doesn't have all these other errors because you've got airflow measurement involved. It's a superior way to do it. It still has problems. You still have to, anytime you use CO2, there is a problem because you're making a lot of assumptions, but the bottom line is what you see there on the right is a lot better than what we're doing there on the left. We're just fooling ourselves, okay? Really, we're just fooling ourselves. And I think it's heavily driven just by people that only care about energy. And we forget about caring about people. Which, the nice thing about me able to do my own recordings, I can say what I think. I think it's really pretty terrible that after the last few years that we dealt with COVID, that we clearly know is, related to ventilation problems, that we're still going around spending most of our time trying to figure out how to ventilate less. I think that's sad, okay? And, that's just how I feel about it. So the one on the right, your uncertainty is basically what's the uncertainty of the flow measurement you have. That's what it is. It's, so there you go. Okay, now control sequences. All right, I got to step aside for a second, get a glass of water, come right back, talk about control sequences, okay? Be right back. All right, now we're going to talk about control sequences, and we're just going to talk about the airflow portion of it. We're going to do recirculating and DOAS with or without DCV, okay? So basically, the most complicated systems are recirculating systems, particularly supply return fan recirculating systems, because you have a lot of choices and you have a lot of issues. So what I want to look at here is, where do you want to measure, okay? And when you take a look at this, it's basically, we want to measure supply flow, return flow, and at least minimum outdoor airflow rates. When it comes to local exhaust, it'd be nice if you measured them all, but it's really not realistic to measure all the local exhaust. Test and balance, go on fan status, probably the best thing to do. There's some considerations for high rises, but we're not going to get into that today. And there's also issues, toilet exhausts are pretty dirty, so you just got to watch. You got to watch that application. But these are the measuring points. We need to know these flow rates, okay? And I'm just going to say that, when you get on a rooftop unit, okay, that's really what I'm talking about here. Rooftop units, they're not really all designed that well to start with. And if the flow rates get below 150 feet per minute, the damper is almost closed. The wind becomes a problem. It'll false out any airflow measurement device you put in there. You won't get to real readings. So we say, if you go below 150 feet per minute, and you have the ability to go min-max, then do it. And we're talking about where the flow meter is. I like to pick air handlers where the dampers are sized smaller than the intake opening, and that's where I want to put the flow meter because the losses are a little bit higher. I mean, it's not a limitation of us. We can measure down to still air. It's an application thing, okay? You just don't want to get these false readings, okay? Now, when people do these supply return fan systems, a lot of times they don't think this all the way through. If you have a supply return fan system that's not relieving air, okay, and you have this, supply and return flow meter that you're probably using to control the return fan for differential flow control, and you're also simultaneously doing outdoor air by modulating, the intake and recirc dampers, you may or may not realize this, but just basic simple instrumentation error is going to make these conflicting loops, and the system's going to hunt, and it's not going to work. So you don't want to do that, okay? What you want to do is you want to, I call it, make the return fan your friend. And here I'm doing it with the outside airflow meter. You could have done it with the differential. It doesn't make any difference to me, except that the outside airflow measurement, even if it was 5 or 10% of reading, is typically more accurate than the differential of even plus or minus 2% flow meters. You could do the math on that if you want. I'm not going to do it today, but basically, let's say you make the return fan your friend, you're basically, you're sequencing the outside air damper, the recirc damper, and the return fan to maintain your outside air set point, outside airflow set point, which, when you're not relieving air, is your pressurization flow set point as well, okay? And so we like to use these diagrams. They're not unique to EBTRON. Just as a way to understand this strategy, particularly when you're sequencing things. A lot of times engineers will write control strategies in a text format that there isn't a programmer in the universe who can write. And so it's much better to use this type of a way to describe the sequence that you want to do. And so we're talking about, right here, we're talking about the outside air flow intake measurement control here. And if you go from left to right on the sequence, the green solid line is basically your outside air damper position between 0 and 100%. The blue dashed line is your return air fan speed, and the purplish dashed line is your recirculation air damper. So moving from left to right, you can see what the sequence looks like. What ends up happening here is we're going to have to find, and I'm going to tell you how, but we're going to in a minute. But we're gonna run a lot of this sequence with the outside air damper in a fixed position, and we like to do that because the outside air dampers are usually oversized and they're very difficult to control. And there's a lot of cases where we need to build up enough negative pressure to suck air in. Just modulating an outside air damper won't always result in getting the right flow, particularly with a supply return fan system. So this blue area, we kind of call this the startup. So why? Well, we're coming out of night setback, so the outside air damper is closed. It takes some time for that damper to get to this fixed minimum position. So we're going to lock our sequence in this purple area. We're just going to try to modulate the return air fan to maintain set point. Now, we like to start with the return air fan at its minimum speed when we're coming out of this night setback mode. Why is that? Well, it's not rocket science. It's basically, hey, return fans can be a problem and they can push air out an intake. So if you start with the return fan at its lowest speed, you're going to have your mixed air plenum pressure at its most negative. So you're going to, when you open that damper, you're going to bring outdoor air in, and that's what you want to do. And then basically, once you do that, you're modulating that return air fan to try and make set point in this blue region while your damper is getting to its minimum position. And basically, one of three things is going to happen. You're either going to hit set point somewhere in that blue area, or you're going to have too much outdoor air, it's not going to be common if you set this thing up right that would happen, but it's possible that you have some crazy wind or stack pressure situation that's going to create more outdoor air than set point. If that were happening, the only thing you could do is modulate, close the outside air damper. And of course, you would never get all the way to this point that I'm at now because you wouldn't be bringing any outdoor air in. But that's the one extreme, and the other extreme, which is a little more likely on a VAV system that's turned down, is that you have the return fan at its minimum speed, okay, but you need more outdoor air. So this sequence will open that outdoor air damper first, and then if you still needed more outdoor air, it could happen. It most likely would happen if you have a min-max arrangement where the min is a little undersized. Then you would basically close the recirc damper. And I just put this little kind of red thing in here that obviously if you close that damper, if you look at this sequence, you'd blow the air handler up, okay? So you don't want to be there, and one of the things that I don't talk about is, where you should put alarms and shutoffs and things like that. I just showed a whole sequence, okay? I'm assuming that people that are implementing this understand that, this would not be where you want to be. But it's the whole sequence. This works very well. We've been doing it for years. An alternate to this would be, I have a really oversized outside air damper. I can't make this really work, and I want to do this a little differently, okay? And I learned about this a long time ago. Dr. Stanley Muma was looking at doing, Penn State was looking at doing outside air control, and he was modulating the recirculation air damper because outside air dampers were so bad and so big and so hard to control. And this works out pretty well too. The startup sequence is the same. There really is nothing any different here, okay? The difference is if I need more outdoor air and the return fan is at its minimum speed, then I'm going to shut back the recirculation air damper to some point. And hopefully that will get us to our set point. If it didn't, we'd then have to look at opening the outside air. And again, I put the yellow in there because hopefully you're not operating in this yellow range, but this is the sequence, okay? So these both work, okay? These both work fairly well, all right? The trick here is how do you determine what the minimum position damper is? And the way that we like to do it, I'm sure there's people that have a different way, but the way that we like to do it is, we'll set the system to 100% supply air. Basically, the return fan we'll put in this, 80 or 90%. A lot of this has to do with fan sizing and if it's properly sized, but in this 80 or 90% range, and then basically we will open the outside air damper until the EBTRON flow meter reads the set point. So those of you that are doing this, make sure that your test and balance people have gone through and are happy with the airflow meter before you start setting things up, okay? Because once you've set it up, you've established this position, and then you're good to go. All right, now that's a very, that's a case when you don't have any relief at the air handler, which is not going to be every system you do, okay? But this is going to be a lot more common. You're going to have a system that is relieving air at the air handler during what we call minimum outdoor air mode. So we're not economizing, but we still have to relieve some air. Okay, when you do that, that's when you start to look at doing your fan tracking or your flow measurement, controlling your return fan to maintain a constant differential between the supply and return. One mistake that I do see people make is a percent differential. Percent's not what you want. It's a constant differential because that's your pressurization flow. If you kept a percent differential, your pressurization flow would change, and hence your building pressure would change. So you go back to those slides I did in the very, very beginning, and we talked about how to come up with set points. You're maintaining that delta CFM set point. Okay, and then on the outside air side, you're maintaining your outside air set point. And I neglected to say in the previous slides, actually in the previous slides you wouldn't be able to do DCV. If you didn't have relief at the air handler at design, you shouldn't be doing DCV. But in this case, we can reduce our outdoor air and still maintain pressure. So in this case, the outside air set point, if it's low occupant density or high occupant density, not big population changes, a fixed set point, basically set that and maintain that. If you're doing DCV, use one of the strategies I talked about to figure out the outside air set point, and then reset the outside air set point. Okay, it's not all that complicated, and it does work well. And you'll see we do this. See on the top left there, we have optional DP or bleed sensor. We take our relief damper simple two position. It's either opened or it's closed. And normally we don't have to do any measurement there, but there are cases where you may want some positive control over. We're basically making an electronic gravity barometric damper. We use either a pressure sensor across it or our bleed sensor across it. And when we get some positive bleed flow, we open that relief damper. Okay. Again, it's optional because you don't always need it. Okay, but it's something to think about. All right, so we got supply fan, return fan, recirculating system here. The sequences are just very straightforward. The more outside air, we start with the outside air. Again, the outside air damper is closed. The recirc damper is fully open. We need more outside air. We open the outside air damper. We get to a point where it's fully open. We still need more. We'll start to close the recirc damper. It's pretty straightforward. Again, we still have that alternate. Okay, the only difference here in this alternate is you don't have a return fan to use as your friend because you're using your return fan to maintain building pressure. So you're simply doing this with dampers. Okay, and it's the same thing we talked about before. All right. One thing is, this is a case where you might want to call me up or say, Dave, you gave me PDF pages of this. I'd really like to see the sequence. So that would be, you'd want my PowerPoint version of it. Okay. And again, you want to be careful when you're in this area all the way here to the right. Okay. The return fan doesn't get any easier than this. You need more differential. You turn down the return fan. Okay, so now we're actively economizing. What's the difference? The biggest difference is where our outside air is being controlled to maintain if we're in a modulating portion of the economizer, okay, the outdoor air is being changed to maintain supply air temperature set point. So you're not really using the outside airflow meter, although you should be looking at it because you don't want to fall below minimum, okay? And that's what I'm kind of going to say here when you see the different colors come up. So this is basically your supply return fan, return fan, recirculating system. You know, what are we doing here for these for the economizer? And basically, I'm going to go right to left this time. Here you're starting. You're basically in minimum outdoor air mode to the right of that vertical line on the right side. You're doing your control strategy for minimum outdoor air, and then as we start to, you know, basically we're in 100% economizer. You know, what you're doing is you're using a cooling coil and you're conditioning that air to get to the supply air temperature set point. Now you get to a point where you know, the outdoor air temperature, you know, really has gotten to the point where you need to reduce the outside air. So it's this economizing mode where we're basically looking at free cooling 100%, and we're going to modulate down here, okay? And we're going to eventually, as it gets colder and colder, cut the outside air back. And honestly, somewhere in here you have to be concerned if you've gone below the minimum, that you shift back into minimum outside air mode. And that's why I say hot economizing or minimum outdoor air mode, all right? Because it could be either, all right? So basically, supply return fan system there, okay? When you have a min-max damper, what you want to be thinking about is, you know, how do you handle the min and max damper? I mean, do you handle it as a single damper when you're doing this? Do you close the min first? Do you close the max first? I think it's very obvious that you close the max first. Okay, so I'm going to go the same way. We're over here. We come down. We were in this economizing with cooling, and now we're in free cooling mode. We're doing the same thing with the recirc air damper. You know, meaning that our outside air dampers are fully open. And now it's like, okay, what do we do now? Well, the first thing we're going to do is modulate, close the max outdoor air damper, and then finally we're going to close the min damper. And you want to be, usually I say to people, and I get some folks get mad at me, but again, they use our stuff for min and max, and that's fine. If you use it for min and max and it works for you, I'm happy with that. But I've seen cases where min and max measurements don't always work well because the max flow can get so low that any little gusts and winds are a problem, okay? So I say you just put a flow meter in the minimum path. If you want to put one in the maximum path and you have a different way of doing it, be my guest. Just remember that if you're in the max path and you're splitting the dampers this way, okay, which you may not be. Maybe you're saying, no, I modulate them both together, and maybe that works out for you. You know, that you're going to get to some pretty low flows where just a little bit of wind could be a problem, okay? So anyhow, you just have to make sure that when you're in this yellow range, you're looking and see that you don't fall below the minimum, because if you do fall below the minimum, you got to shift back to minimum outside air mode, okay? All right, and if you're in this area doing the sequencing the way I want, it's more, I don't know that you always really know the outside airflow rate. That's all that's about there, okay? The supply fan, return fan sequence for the fan, it's pretty much the same, no different. I need more of a differential, I reduce the return fan, okay? When you get to a relief fan system, you know, this is a kind of, you know, this is one of these presentations that's kind of hard to listen to and hard to give, okay? Because it's just boom, 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 boom. I will tell you why I picked now to tell you that we are working on, you know, technical bulletins to kind of put this in print, okay? So it's a little easier to digest. But, right now this is what I've got. It's a presentation, so, and I'm moving pretty quick, all right? So when I have a relief fan, I don't do a whole lot different, okay? The measurement requirements are exactly the same, okay? Supply, return, and outside air, at least minimum outside air. And I need to know something about the toilet exhaust, okay? If I don't have any relief at the air handler, well, I don't have a return fan to be my friend, but then I also don't have a return fan to be my enemy. So I'm just going to be modulating the outside air and recirculation air dampers to maintain my set point. It's pretty straightforward. It's just a sequence. It's just like we talked about before, and that'll maintain your set point. Okay, the same alternate strategy where, hey, the outside air damper is too big, it's not reliable, we'll use a recirc damper, the flows are higher, it's easier to control. Same thought process that we talked about with return fans, okay? And so I'm going to fly through this. It's not any different, all right? When we go to active relief, it's pretty much the same thing as when you have a return fan. The beauty of measuring airflow rates is if the airflow rates are right, you're going to be relieving air. If these flow rates are right, you're maintaining the proper differentials, you're going to be relieving air. Some people look at that and they're like, well, you're going to be sucking air through the relief fan. No, then the other flow rates wouldn't be right, okay? So you wouldn't be maintaining your flow differential. So as long as you're maintaining your flow differential and your outside airflow set point, this works fine, okay? And the sequence is simple. It's the same old sequence we've been talking about for increasing outside air. There's no return fan, so it's not part of the sequence. The setup is a lot easier. I do like supply return fan systems though, okay? And the alternate, guess what? A lot of repetition here. It's the same, okay? So that's the good part. You find that there's really not a lot of differences, in these different methods, but these are the measuring points that you really want to use, okay? And nothing's any different here for controlling the relief fan, okay? As when we're going into an economizer, when you look at the economizer, nothing again is any different. We're instead of controlling the return fan to maintain the differential, we're controlling the relief fan to maintain the differential, and we're modulating the intake and recirc dampers and maintain our supply air temperature set point. So nothing again any different. I'm just going to fly through these slides. It's the same slides we already looked at for when we had a return fan, okay? No different. All right. So that helps me speed this up a little. No difference on the fan control, okay? Now, I'm not going to do the sequence drawings for this. Because it's pretty easy, all right? When you have a separate relief fan, you're not relieving at the air handler, all right, which is pretty common in a lot of areas. You're basically, you're bringing in the outside air you need, and you're make sure it's above what you're relieving, and then you maintain your delta CFM to maintain pressure. And the thing that I want to caution everybody on here is when you do the math and look at how accurate the flow measurement needs to be to do differential flow control, you find you need very accurate flow measurement, okay? And so that means that you have to pay more attention to where you're measuring the outside air and where you're measuring the relief air. When you're doing minimum outside air for dilution ventilation, for air quality, I think 5 to 10% of the actual flow is a good reading. But when you're doing it for pressurization and differential tracking, it's not. It's 5 to 10% is not good enough. And again, I can show you that. I have plenty of material to demonstrate that. But you have to get to some, you got to be in that 2 to 3% range, and sometimes even more accurate. It depends on how much how much outdoor air you're bringing in and what your pressurization requirements are. But you have to have accurate measurement. The same thing's true on a relief fan. I mean, if it's a ducted relief, that's great. But if it's just a relief fan hanging in the ceiling, it's going to be really hard to get a good measurement here. So you just have to pay attention to it. This here we see a lot of times. Maybe there's no economizer, or maybe there was a water side economizer, or maybe it's not really serving air handlers, but it's VRF serving fan coils. The bottom line is we have to bring outside air into these spaces. Doesn't matter, the system's different, but we still have to bring it in. And a lot of times we'll see people just totally ignore the flow measurement into these fan coils, which are in a lot of cases variable speed fan coils, or variable speed air handlers, or doing DCV where the outside air set point varies, and it's like, you have no control of this. So what you want to do is you want to measure and control the flow, the outside airflow into these units. And it's just the way we talked about. If it's fixed, it's fixed. And if it's DCV, then we're going to use one of those DCV strategies. And in a lot of cases, it's going to be a combination of fixed and DCV, okay? You're just not going to pull this off and have a building that works very well if you're not measuring and controlling these airflow rates. So the good news is it's pretty straightforward. You're modulating a damper. There's no complicated sequence here, all right? But basically, that's what we want to see people do. And honestly, there's a lot of buildings out there that are not doing that. And then, or there's people that say, well, I'm going to use my, VAV box kind of flow meter. Well, I wouldn't do that, okay? Particularly if you're doing DCV and you got a lot of turn down, because you're not going to get good measurement, okay? So we have products for this. You should look at it, okay? And I probably upset people here when I say this is my least favorite, but the one thing I hate is when I see air handlers serving 10 floors above or 10 floors below. One central station, bunch of air handlers serving multiple floors. It's a control nightmare, okay? It's got stack effect problems, stack pressure problems on the floors. To me, they're very complicated. And what we tell folks all the time here, it's like, look, you got to get your outside air under control. No question about that. But you also have to get your floor pressure under control. And, that means you need to look at differential flow control on the floor level. You might reset it to static pressure to handle seasonal changes in stack effect. You do not want to ever sum the VAV boxes to get the total supply. You really want to measure the supply flow there. The return flow, often depending on how the building's designed, there's no place to measure. If we get in early, we at least ask people to do some kind of stub ducting system. That works out pretty well. You use our Air IQ1 on those. It's a damper flow meter, just a stub duct for the return off the floor. And you maintain a differential, okay? If you don't do that, think about what you're doing. I mean, if you're not doing any control of the return flow, you've got, in a lot of cases, 20 floors of stack pressure that is completely uncontrolled. It's a big hole in the building, okay? So, just things to think about. I do this one with a relief fan. It's pretty much not really any different, okay? Now we get into DOAS, okay? And DOAS, particularly with energy recovery, okay? Single zone, you want to measure the flow into and out of the zone. And it may not be, you may be providing plenty of outdoor air. And you may not be that concerned about that. But what you do need to be concerned about is maintaining the differential. And it's like, well, no, I just run it. Well, what happens as filters load? What happens as wind pressure changes? What if there is a stack pressure effect? How are you handling it? What if it is DCV? How are you doing this tracking? And so, the right way to do it is you do differential flow tracking, okay? And I've seen people do it on multi-zone. I don't like it because it's multi-zone. It's like the individual zones that they're changing. This isn't going to work out very well. But certainly on single zone DOAS, this is what you want to do. When you get into multiple ventilation zones, a much better way to do it would be to, basically do the same kind of tracking, but also do something at the zone level, okay? And a lot of times I'm looking here, you're doing DCV. DCV really needs this to happen, okay? DCV really needs there to be continuous tracking, because as one ventilation zone changes, the other ventilation zone will change as well, unless you're controlling the flow rates. Okay, so this is one way to do it. And notice here, it's the same thing if you're using good flow measurement. I am not against you summing individual EBTRONs to get the total supply. So it's similar to the previous slide. It just depends on how you want to do it. Sometimes people want to get the flow meters in the energy recovery unit and then just ship that way, and that was the previous slide. This way is now I'm doing it out in the field and I don't really need that extra flow meter. When you get into really humid climates, deep south, particularly when you're doing DCV, if you're not I know this sounds excessive, but this is true. If you're not tracking the flows into and out of each ventilation zone on DCV in the south, then you're going to have pressurization problems. And you might bring in plenty of outdoor air, but you're going to have moisture problems. And I've seen firsthand buildings that have plenty of outdoor air, schools in particular, plenty of outdoor air, where the walls are soaking wet. And this is why. They're not controlling the flows. Okay, so you need to really get that under control. Okay, I think that was pretty fast, but it should give you an idea of what we can do and what we know and how we can help you. So if you want to go more into this, we're available to help. Okay, all right. See you later.